Good evening, everyone. I'm Gordon Ringgold. I'm the newest advisory board member for Café Scientifique. I'm a local biotech guy, ex-Stanford professor, but I've been spending the last nearly 3 years working with UC Santa Cruz to establish a satellite campus on this side of the hill. We manage a large program in collaboration with NASA Ames. So I was asked to join the board about a month ago, and 10 days ago I got an email, "Can you find us a speaker for April 9th?" I said, what kind of organization did I just join? But I'm delighted that we were able, and it's just by chance that Greg Laughlin was available this evening. Greg is a graduate of UC Santa Cruz, and I'm going to ask you a question. You know the answer now. How many of you know who runs the Lick Observatory up on Mount Hamilton that you all see every day? UC Santa Cruz. If you ask most people in Silicon Valley, say, I don't know, is it Stanford? And as a recuperating Stanford professor, I disavow any of that, nor Berkeley. And UC Santa Cruz also runs the Keck Observatory in conjunction with Caltech. So we have one of the strongest astronomy, astrophysics groups in the world who have made brilliant innovations in telescope design and adaptive optics, and you're going to hear other aspects of what we do. Greg is a graduate of our Ph.D. program, postdoc in Tokyo, in Michigan, joined NASA Ames as a research scientist, was then recruited to our faculty, and in a meteoric rise, and that is not a pun, was promoted very rapidly to associate and full professor, where he is now chair of the Department of Astronomy. His interests really are in detection and characterization of extrasolar planets. He's one of the lead investigators on the NASA Kepler mission, which is on the front pages of the newspapers quite regularly. Hydrodynamical simulations, which I have no clue about at all as a molecular biologist. And I think the topic for tonight, also in the extremely distant future, he wrote a popular book with Fred Adams, University of Michigan, called The 5 Ages of the Universe Inside the Physics of Eternity. And it's a popular book that I think is being updated. And so I'm just delighted to be here and to introduce Greg Laughlin.
Thanks, Greg. Well, thank you very much for inviting me on short notice. Luckily, it wasn't like April 1st when they did that extra speaker. It's always great to see an audience of interested faces at a public lecture, so it's a real honor for me to be here. So I thought I would start out with, at first glance, a completely boring picture. It just looks like the blue slide of a background. But it is a picture, and I took it myself, and I took it from my front steps of my house. And you can see the power lines down there in the lower right-hand corner. And there's 2 other things in the picture that you can see. These are mirrored. But there's the Crescent Moon right here. It was very beautiful. And this is just with an ordinary, just regular camera. And then up there in the upper left-hand corner is Venus. And it was just beautifully shining in the nighttime sky. The human eye is more sensitive than a camera. It has a better dynamic range. And so while this scene looks sort of washed out, in the picture, it was really beautiful and remarkable and, in a sense, awe-inspiring. And it's really kind of interesting to think that when you're looking at Venus in the night sky, or in the early evening sky, that you're looking at a world which is nearly the size of our own. If I sort of shrunk the solar system down to a size scale where the Earth is like a grain of sand, then the Earth is a grain of sand, and the sun is like a dime held at 2 arms lengths, and Venus would be another grain of sand held roughly just a little bit to the right of my nose. That's sort of the scale of the solar system. And this is kind of a cool picture as well. This was during the transit of Venus, when Venus passed in front of the sun. This picture was taken in 2004, but it also happened just last year, just last June. Probably many of you saw the transit. It was visible from here. And this is the sun. This is clouds in front of the sun. And right here, you can sort of see Venus just starting to transit, make its trip across the sphere of the sun. And there you get a sense of the size scales involved. Venus is much closer to us than, sort of 70% closer to us than the sun is, but it's still quite small, even with it in the foreground. It's quite small in comparison to the sun. If we line them up and looked at them from a very, very long way away, Venus would be about 1/100th the diameter of the sun. And the Earth is also 1/100th of the diameter of the sun. And so if you just watch Venus from night to night, you see that it's an evening star. It has this kind of odd path in the sky from night to night. And then later you see it in the morning with another odd path. And it shows these kind of weird seasonal cycles that are not in sync with the seasonal cycles on Earth. It seems to be following its own rhythm. It's hard to understand what it will do next, but in the same sense, it's completely predictable. And that kind of segues into the topic that I wanted to talk about tonight, and that is the idea of prediction. How can we predict what Venus will do years into the future, thousands of years into the future? How far can we predict Venus's motion? And how do we do that? And so the first breakthrough, in essence, with predicting what Venus would do came from Kepler, who discovered empirically by kind of charting Venus from night to night and looking at historical records of where Venus had been in the sky and also comparing it where the other planets had been in the sky, Kepler realized that the planets trace elliptical paths around the sun and that the period of a planet depends on how far away from the sun it is. Kepler worked out these laws of planetary motion, but he didn't understand what was going on in the sense that he could say what Venus will do for some time into the future to a reasonable degree of approximation, but he couldn't explain the why. And part of making a really satisfying prediction is to have an idea of what the why is and then see it unfold in a correct manner. And it was really Isaac Newton in the 1680s who cemented our ideas of what the why is, why Venus is doing what it's doing. Here's Isaac Newton. And this is a picture from Isaac Newton's great book, The Principia. And what it does is it gives us a sense of the why. So this is kind of a thought experiment here. What we're seeing here is we're imagining that a sort of a very tall mountain is built on the Earth. And you go to the top of that tall mountain and you start throwing a projectile. Now, if I take a projectile out of my pocket and I throw it, if I toss it, it will make a parabolic arc through the air and it will land on the floor a little bit to my left. And if I take an object and throw it hard, sideways, it will make a more relaxed parabolic arc and it will land further to my left. And so you can imagine that if I take something and I throw it with incredible sideways speed, if I give it a large tangential velocity vector, as it falls towards the ground will curve out from underneath it. And in fact, if there was no air resistance, the ground would just continue to curve out from underneath it, and it would be in orbit. That's the basic, what's going on with an orbit is it's an object in continual free fall. And what Newton realized is that Venus is, in some sense, well, not in some sense, but Venus is continuously falling around the sun, endlessly. And upon doing that, he was able to make sense of what's going on in the solar system. This picture is hard to see. Sometimes things look great on the laptop screen and they just don't translate to the screen. And so when that happens, you just have to listen to what I say and not focus on what's on the screen. But what's on the screen, this is where the planets in the solar system are right now. I computed their locations right at this very moment. And they're all going around the sun. They've been going around the sun for 4.5 billion years. And the question is will they continue to do that? Now that seems sort of like an obvious question. And obviously tomorrow they're going to be continuing to go around the sun. And obviously tomorrow the sun is going to come up. But we can ask questions like, for how many nights can we expect that the sun will continue to set, and for how many mornings into the future will the sun continue to rise? That's a valid question. We know that the answer is large, but what is the answer? And so to motivate the idea of the fact that the planetary orbits might not be sort of as stable and as clockwork-like as we would perhaps like, this animation, which is also hard to see, I apologize for that again. These are 3 extrasolar planetary systems that have been discovered in the last 5 or 6 years. And what's going on here is I've taken the planetary systems, each one of them has 2 or more planets, and sort of follow their equations of motion forward into the future. I take the equations that Newton wrote down originally that explain the motion, and I just project the system into the future. Now, when I do that, in addition to these planets falling around the parent stars, the planets are also pulling on each other. The sun pulls gravitationally on the planets, and the planets pull on each other. And in these systems, over thousands of years, and what I've done here is I've sped the motion up. So I'm not looking at the individual trip around the sun, but I'm looking at hundreds of orbits sort of strobing snapshot after snapshot. So I'm showing thousands of years of system evolution here rather than one trip around the star. And when we look at these systems over thousands of years, hope that's not my phone. If we look at that system over thousands of years, we can see that there's kind of a lot going on. This particular system, HD 128311, has 2 planets, and they are not happy with what's going on here. The orbits themselves are oscillating in and out and precessing and literally crossing each other's orbits. Now, of course, if 2 planets have their orbits cross, that's okay as long as the 2 planets don't arrive at the same place at the same time. And so interestingly, in this particular system, the planets have worked out, if you will, an agreement not to run into the same place at the same time. It's a marvel that Newton's laws of gravity allow the planets to communicate without any sort of intelligence, but just naturally through the laws of physics, communicate in such a way that they never collide. And in fact, in our own solar system, Neptune and Pluto are doing exactly that. Pluto goes around the sun 2 times on average for every 3 times that Neptune goes around, and they never arrive at the same place at the same time. Pluto's orbit certainly is tilted up slightly, but they never arrive in a projected manner in the same place at the same time. They're in what's called a protective resonance. And then you have a system like this one where it's not so crazy, but there is also not sort of a protective lock on the system. The orbits are going around, and it's not clear whether this system will last for the duration. In fact, if I were to continue this integration, instead of just looping it over and over again, if I was going to kind of continue it all night, come back in the morning, there would be a very good chance that those planets would not be orbiting that star anymore, that there would have been a collision, or there would have been an ejection, or something rather dramatic. And so we see this first-hand evidence when we look out at other solar systems, which we can do now. We can detect other solar systems, and we see that all is not necessarily well in all these systems. And that brings us back to a problem that has a 300-plus year history, and that is the stability of our own solar system. So Newton himself realized that the planets pull on each other through the laws that he wrote down, and he knew from observations that our solar system at that time was doing a curious thing. It looked like Jupiter was moving inwards ever so slightly, and Saturn was moving outward ever so slightly. So that within a few thousand years, if this motion continued, or maybe a few tens of thousands of years, if this motion continued indefinitely, the solar system would be destroyed because Jupiter would sort of spiral into the sun and Saturn would spiral out. And Jupiter, in spiraling into the sun, would wreak havoc on the inner planets. Newton could see that this was happening. He could see Jupiter slowly spiraling inward, Saturn slowly spiraling outward. And he tried very hard to use the equations of motion that he developed, his law of gravity, to figure out what was going on. You can use the law of gravity to explain that 2-to-1 lock that I showed, or to explain the Pluto-Neptune motion. He tried to use it to explain what was going on with Jupiter and Saturn, and he couldn't do it. Newton was perhaps the finest mind of the last 1,000 years, and he couldn't do it. And in fact, he wrote that to consider simultaneously all these causes of motion, that is, pulls between the planets as they go around the sun, and the sun's pull on those planets as they're pulling on each other, and to define these motion by exact laws, admitting of easy calculation, exceeds, if I am not mistaken, the force of any human mind. So that's a big deal, right? You have the finest mind of the past 1,000 years saying that solving this problem exceeds the force of any human mind. And what Newton did was he actually kind of brought God into the mix. And so he said that it's proof of divine providence that we have a solar system sitting here. That means that God is coming in every few thousand years and setting things right. What more proof could there be? Right? So it's kind of an interesting existence proof for a benign deity. And so this really kind of threw down the gauntlet for successive generations of mathematicians. And in particular, in France, after Newton sort of laid down the ground rules, the French mathematicians took Newton's laws and they developed them to an extraordinarily high degree of art.